our session for today. And I am going to go over the quiz very briefly. So I'm not going to show the detailed solution, but a lot of you did great. So good job to you guys. Treat yourself well. And some of you were okay, and there's just few of you are getting there. So that's still a good start. So I'm happy about the results. So that's good. And you guys should be happy too. If you're studying, you should feel good about it. Okay, so let's go ahead and start talking about the quiz briefly, and then we'll start our session for today. So here's the quiz that you took last night. Of course, the questions are not in order, so ignore the numbering. So let's go back. All right, so for the first problem, this shouldn't take you, well, for me, it's the first problem because that's what I typed in. It shouldn't take you more than a minute or two, or a minute and a half, right? Because you just have to look at the equation and identify which of the following statements are true. So you're not really solving it, right? So what do you guys think about this differential equation? So if you want to speak to your audio, please do that.
It's a linear.
Right, so if you look at the equation, we can rewrite this. This is dy dt minus 2y equals to negative t cubed. That's in the form of a linear equation, right? Y is by itself, the derivative is by itself, and you have a function t cubed. It doesn't matter, it's linear in y. So this is check. Now, is it separable? Can you separate t and y with its differentials?
No.
Right, so this is not true. What is the order for this equation?
First order.
Professor,
Right.
why isn't it separable?
So it's not separable because if you try to separate t and y, I would multiply by dt on both sides. So you would have dy minus 2y dt is equal to negative t cubed dt, right? Now, this is the problem. How do we separate this? We can't, right? We have y with dt, so there's no way we can isolate a function of t with dt and a function of y with dy. So that's why it's not separable. I hope that makes sense. So the order is first, that means this is a choice. Now we already said it's linear, so that means the fourth option is also not a choice. So therefore the first statement is true, okay? And that shouldn't take you too long, maybe a minute, a little bit more, but that's first one. Then the next problem you had was to determine which of the following are separable. So you quickly want to check, can you write a function of x with dx and a function of y with dy? Is the first one separable? So Sadia H, you said all of them, they're separable. Yes, the answer is yes, they're all separable. So again, you just quickly check, can you separate a function of x with dx and a function of y with dy equals to, whatever constant, 0, whatever you have. If we are able to do that, then it's separable. Again, you're not solving, so just going down the list doesn't take you too long. So these two questions probably have taken you at most 3 minutes. Number 3 is the one you have to solve. So this should have been taking you a good 3 to 4 minutes, or maybe max 5 minutes. So I'm going to hold on to 3. Let's go down to 4. Let's determine the interval in which the solution of the differential equation has a solution is certain to exist for the initial value problem. So how do we approach this question? Does someone help me out?
I use the integrating factor. Integrating factor.
Well, are you solving? So you don't have
Well,
to solve this one, right?
oh,
You could use the 2.4 theorem.
Exactly. So this is the time you want to recall theorems, right? So I didn't give you a number or a hint, but it should give you a hint when you're looking for an interval. We're actually using a theorem to guarantee us that the initial value has a solution. Okay. So this is referring to theorem 2.4.1 or 2, the first theorem that we talked about in this section. So what you have to do is determine where is P of t continuous and what is G of t continuous. That's what we want to determine. So P of t is this function right here. That's P. And G of t is this function right here. So G is continuous everywhere because it's a polynomial of degree 2. What about P of t? Where is P of t continuous? So what do you think?
From negative infinity to negative 1.
Mm-hmm. And then?
From
So
negative
P
1
of t is negative 1 to 1, right? And then, so P of t is this function, t over 1 minus t squared. So if I were to factor the bottom, I would get 1 plus t and 1 minus t, right? So discontinuities are at 1 and negative 1, right? So those are the one you remove from the domain and it makes it continuous everywhere. So 1 to infinity. Now, what is our t naught? What is the initial point? That's negative 2. And it falls into which interval?
Infinity to negative 1.
Exactly. So that's the interval where it is certain to have a unique solution. Okay, so the answer to this problem would be the interval negative infinity to negative 1. So again, this problem, you don't have to solve it because we're not looking for the solution. We just want to know where is the interval where there is a guaranteed by theorem we have a unique solution. Okay, so again, no solving to do for this problem. The only problem you have to solve was number 3. So this should have been again another quick question. So it's taken you most maybe 3 minutes or 2. And number 3 is, what kind of equation is this one? So let's check this out. Right, so Sadia, you said it's homogeneous, and you're absolutely homogeneous, right? It's not separable. And then we talked about linear. It's not linear because we have y squared, so it's homogeneous. So I'm going to rewrite it. So we have dy dx is equal to xy over x squared plus y squared. Now, to make it homogeneous, we want to express the derivative as a function of y over x, right? So I'm going to go ahead and divide each term by x squared. So we have y over x on top, and on the bottom we have 1 plus y over x squared. So I have expressed the derivative as a function of y over x. Okay, so that means it is homogeneous. Or you can plug in the substitution, x equals to k times x and y is equal to k times y. Simplify, you should get back the original equation. That will also be a way to determine it is homogeneous. So now that you know it is homogeneous, all you have to go through is finish the question using appropriate algebraic skills. Okay, so we use the substitution v equals y over x. So that means dy dx is equal to, so I like to write it this way, y is equal to v times x. And then you can differentiate that using product rule. So you would get v plus x dv dx. and then you just continue. So I hope that makes sense. Let me know if you guys have any questions. Okay. Anik?
So, Professor, so you divided the denominator by x, and the bottom you divided by x squared, right?
No, I divided the entire equation by x squared. So if you look at
Oh
this
yeah,
term,
yeah,
I
I got it.
divided by x squared, right?
Yeah.
Yeah. And then I simplified it. Yeah. Now, you should know how to continue this problem and then simplify at the end. Now, which one of these come out to be the answer after you simplify? So, right, so Sadia H, I would say definitely practice so that you can time yourself finishing this question within 5 minutes limit. I would say that because I worked them out and it didn't take me so long. So I timed double of that time for students. So I think that's reasonable. And if you do the homework, if you study the materials, if you review our class notes, you should be okay with the timing that I give you. And I have an intention why I give you that much of time so I can prevent student not getting off the quiz or cheating and all of that stuff. So, so just be honest with yourself and work through this question honestly, okay? And just make sure you're learning materials. That's the purpose of taking a course, right? So for this question, so what's the answer to this question? Those of you who got it right. What do you guys think? Greg, I remember you said you solved it. Was this the one you solved?
It was the first choice, I believe, with ln y minus x squared over.
Mm-hmm. So when you solve it, you get right. So this happens to be the answer after simplifying everything. Okay. So see, those of you who didn't get it right or you think you didn't get it right, let me know if you can finish from where I stopped. And if you want me to go through it next time, I can do that next class. Okay. So there you go. That's our quiz, first quiz. Hopefully you guys have fun. All right, so I'm going to go back and continue our lesson for today. So just briefly, let's talk about what we did last time. So we talked about a solution in a tank. So if you have salt, water mixture coming in and mixture exiting, we want to measure or keep track of the amount of salt that is inside the tank. That's the idea of this problem. And then we talked about some notation, units, and then I derived the formula for you guys. We want to measure the rate. So the rate is equal to rate in minus rate out. So the rate in we can measure by what's the rate of liquid coming in and concentration coming in minus the rate out times concentration out. Okay, so that way we can write all of these down using symbols. We have Rn times Cn minus R out times concentration out, and concentration out is given by this formula, Q of T over V of T. Q is the amount, V is the volume, and because if the rate in and rate out is different, that means it's a linear function that the volume is going to change. So we then determine this formula for V of T is initial volume plus the rate in minus rate out, which will be your slope times T. So then we have this equation, dq dt is equal to Rn times Cn minus R out times Q of T over V naught plus the slope times T with the initial condition Q of 0. Any questions? Okay, so so I'm gonna finish up this problem that we started yesterday. So we wrote down what was given to us. So this is continuing from last time. So hopefully you had some time to meditate on this question. So for the first part, let's find the amount of salt, which is Q of T, in the tank at any time T. So we were given the initial condition at time 0, we have 30 pound of salt. So were you guys able to? So, all right, so I'm gonna finish up this question and then we'll do another tank problem. So for part A, you want to find the function Q of T. So we set this up. We have dq dt, which is given by the formula rate in, concentration in, minus rate out, concentration out. And we rewrote the formula for concentration out. So we have Rn. So for this problem, we have 3. Concentration in is 1 minus R out, that's 2, times C out. Well, C out is Q over V. So that would be Q over 100 plus T. Any questions? So someone has their audio on. If you don't have a question, please mute your audio. Okay. So if you have questions, let me know and you can turn it on. So here's what we have set up for this problem. So we have dq dt is equal to 3 plus minus 2 q of t over 100 plus t. So that's the differential equation we're going to solve. Now, we're going to solve this by using the method of integrating factor. So we have dq dt plus 2 over 100 plus t. Q of t is equal to 3. So we determine integrating factor mu. So mu of t is going to be e to the integral of, so I'm going to pull out the 2, 1 over 100 plus t dt. So this would give us e to the 2 ln of 100 plus t. And if you simplify this, this is just 100 plus t to the second power. So that's the integrating factor we're going to use. So that means our differential equation is going to be the derivative respect to t times mu, which is 100 plus t squared times q of t equals to 3 times 100 plus t squared. And we're going to go ahead and integrate both sides so we can solve for q of t. So we have q of t is equal to, well, 100 plus t squared. So on the right side, when you integrate, you get 100 plus t to the third power plus the constant c. And then by dividing by 100 plus t squared, we have our function q of t is equal to 100 plus t to the first power plus c times 100 plus t to the negative 2. So that's the function q of t. But we have to find what is c. So we apply the initial condition, which is q of 0 is 30. So q of 0 is 30, which implies that what is c equal to? So were you guys able to get a value for c? So what is C? So if I just finish up my computation, I have negative 70. Let's see. Okay. So Liana, you have 3,000 for C. Let's check that out. So if I subtract 100 from both sides, I have negative 70 is equal to C over 100 square. So that means C is equal to negative 70 times 100 square. And of course, you can simplify that. So yeah, I wouldn't say 3,000, right? So looks like it's going to be negative 70 times 100 square. Well, if you simplify this, that's 70 times 1,000, right? Yeah. No, one more zero. So that would be, yeah, negative 70 and then 0, 0, 0, 0. So that's C. But I'm going to use this notation because it looks better. So what is our Q of T then? So our Q of T for part A, it's going to be 100 plus T. So what is this equal to? So it's going to be 100 plus T plus C, we just computed, that's negative 70 times 100 square times 100 plus T to the negative 2. So that will be the answer to the first part. So any questions up to here? Okay. All right. So what about part B? What do we want to compute for this second part? We want to know the time when the tank is full. So how do you approach the second part of this question? When will the tank be full? So if you look at it, initially its capacity is 150 gallon, right? So right, so when it reaches its maximum capacity, which is 150 gallon, so we want volume to be 150. So we want V of T to reach 150, because that's when it's going to be full. But what is V of T? V of T is this function we came up with right here, is 100 plus T. So we have V of T is 100 plus T equals 150. So that means it's going to be full when time is 50. So that will be the answer to the second part. Let me know if you guys have any questions. Now, I'm going to add another part to this question. So let's call this part C. Okay. Let's find the amount of salt in the tank at the moment the tank starts to overflow. Okay, so how do you think you're going to answer this part of the question? Okay, so see, right here. Okay, so for the second, part C, we want to know what is the amount, meaning Q of T, when it is going to start to overflow, right? So what do you guys think that means? All right, so Carolyn, you're absolutely right. Plug in T equals 50 into Q of T. So we already know the function that's going to measure how much salt in the tank, that's Q of T. We want to know when it's going to overflow. From part B, we know it's going to start to overflow when time is 50. So if T is 50, then we know it's going to overflow. So we want to know the amount. So plug in T equals 50. We have Q of 50. And that will tell us the amount it's going to overflow. And we know the model, that's right here, part A. So that will be 100 plus 50 minus 70 times 100 squared times 100 plus t to the negative 2. So if you plug this in a calculator, you'll get the amount of salt when it starts to overflow. But for our course, this is good enough because you're not allowed to use a calculator, so you'll leave it in a setup form. You don't have to get an actual value. But for web work, I think you have to get an actual value, so you can use your calculator for web work. That's
Professor,
uh-huh.
was there a reason why you left t in 100 plus t to the negative 2?
Oh, because I made a mistake. Thank you.
Oh, okay, no problem.
Yep, perfect. Thank you, because we're plugging in t is 50, so 50 goes everywhere there is a t. Thank you. All right, so I'm going to add another part to this question. Okay, so let's call this part D. Find the concentration at the moment the tank begins to overflow. Okay, so what is this one asking us to do? What do you guys think? So, any suggestions?
Using what we found in part C and how much the total volume is, we just put one over the other for the concentration.
Exactly, right? So we want to know the concentration when it's going to overflow. We know when it's going to overflow, when T is 50. So we want the concentration when T is 50. But we know concentration is Q over V. So we want Q of 50 over the total volume, which is 150. And Q of 50, we found it in part C. So that's from part C, right, over 150. That will give us the concentration when it's going to overflow. So any questions on any of the parts for this question? Okay. How do you guys feel? Are you guys okay? Okay, I'm gonna take that as a yes. All right, you guys are very quiet today. So I'm gonna do another problem. So let's set up the second example for tank problem. So here's a example 2. So a tank initially contains 120 liters of pure water. Okay. So a mixture containing a concentration of gamma gallon per liter of salt enters the tank at a rate 2 liters per minute. The well stirred mixture leaves the tank at the same rate. Okay, so that's another scenario to consider. So here are the parts to this problem. A, write a differential equation with its initial condition. Okay. Part B, solve for the amount of salt at any time t. C, we want to, okay, let's see. Let's write an expression for the concentration of salt in the tank at any given time t. And one more part. So part D, we want to find the limiting amount of salt in the tank as t goes to infinity. Okay, so I will give you a minute to just see how much you can do for next 1 minute. Okay, so let's start thinking about this question. So gamma is just an unknown constant, okay? So that's our concentration in just any number, gamma, okay? So for this problem, so let's highlight what's given to us, okay? So we have 120 liter. So this is important, right? A mixture containing a concentration of gamma, so that's just a number, right, of salt enters the tank at a rate of 2 liters per minute. So we have concentration in, rate in, it's well stirred and leaves the tank at the same rate. So rate in and rate out is the same. So let's write out the differential equation for this. Now another thing to keep in mind is it contains pure water. What does that mean?
That means that there is no salt at first. Like
Right, so
the initial value of salt is 0.
yeah, exactly. So this means that initial condition is 0. Q of 0, 0. Initially, there's no salt. Okay, so good. So let's write this down. So what is given to us? So we're given Q of 0 is 0. So initially contains 120 liters. Okay. So we have concentration in. So Cn, that's some gamma, right? Whatever that number is, it's gamma. And we have rate in, that's given to us as 2. And it's well stirred and leaves at the same rate. So rate out is also 2. Okay, and we know the volume, so initially it contains that, so I can just call it V is 120. So your rate in, rate out is constant. That means the volume is always 120. Constant, right? Constant rate. Constant volume, sorry. So now let's set up the differential equation. So part A, we want dq dt. That's going to be rate in to concentration in gamma minus rate out, that's 2, concentration out, that's Q of t over V of t. Well, what is V of t in this case?
Just 120.
Yeah, right? So if you were to compute it like in linear equation, you have 120, that's the initial volume, plus rate in, that's 2, rate out, that's 2, times t. So it's really 120 plus 0t, that wouldn't affect, right? So it's just 120. So our dq dt, it's going to be 2 gamma minus 2 over 120 q of t. And then you can simplify this. So we can say this is 2 gamma minus 2 over 120, that's 1 over 60 q of t. So that would be our model with the initial condition, initial salt is 0. So that's part A. Any questions up to here? Okay, now part B is for you to solve. So that means we're going to solve this. So this is a linear first order, right? So we're going to have to find integrating factor. So dq dt plus 1 over 60 q of t is equal to 2 gamma. So what is mu of t? Mu of t is e to the integral of 1 over 60 dt, which is e to the 1 over 60 times t. So that means our differential equation is the derivative of mu of t, e to the 1 over 60 times t times q of t equals 2 gamma e to the 1 over 60 t. And now we integrate both sides respect to t. So that will give us e to the 1 over 60 t times q of t is equal to 2 gamma. Now, if you integrate e to the 1 over 60, what do you get? This is going to be,
Basically multiplying by 60, so it should be 120.
yeah.
Oh wait,
So
no,
let me just,
altogether. 60 times
yeah, altogether. Yeah. So that will be altogether. So that would be 120 gamma e to the 1 over 60 t plus a constant c. And then we can solve for now q of t. So q of t is equal to 120 gamma plus c e to the negative 1 over 60 t. That's the model. And now we have to find c by plugging in our initial condition. So that would give us, so plugging in t equals 0, the exponential will go to 1. So we have c is equal to negative 120 gamma. Okay? So therefore, our model is going to be q of t is 120 gamma minus 120 gamma e to the negative 1 over 60 t. So that will be the answer to part B. Okay. So any questions up to here? So this is part B. Okay. Now for part C, we want to express the concentration at any given time t. So how do you find part C? What do
Isn't
you
it
guys
just
think?
Q of T over V, the concentration?
So we know, right, thank you. So C of t, we know it's going to be Q of t over V of t. Well, V never changes for this problem, so it's always going to be a 120. So we already found Q of t, that's part B, 120 gamma minus 120 gamma e to the negative 1 over 60 t over 120. And if you simplify, this is just gamma minus gamma e to the negative 1 over 60 t. So that will be the concentration at any given time t. So it's an expression. Okay. So let me know if you guys have question for part C. Now, what about part D? So let's go back to part D. Okay. So what do you guys think for part D? How do we approach this part of this question? So we want to find the limiting amount of salt in the tank as t goes to infinity. So what does that mean? So right, so Sadia H says we have to take the limit of Q of t, right, because that represents the amount of salt in the tank, as t goes to infinity. So thank you, Sadia. So we take the limit as t goes to infinity of Q of t. So that's going to be the limit as t goes to infinity of 120 gamma minus 120 gamma e to the minus 1 over 60 t. So what is this limit? So as t goes to infinity, what happens to this limit?
Professor, doesn't the E basically turn into a 0 if it's to the negative infinity? So it should be just 120 gamma?
Yep, absolutely. So as time goes to infinity, the amount of salt settles to 120 times gamma. Okay, so that would be the answer to this. All right, so thank you, those of you who are participating. Appreciate it. So let me know if you guys have any questions for any of these particular parts. And of course, every scenario is slightly different. Just make sure you read the question carefully and try to see what is the question asking you to find and how can you relate the variables to that specific question. So Jay, yes to your question. So the exponential part to 0, right? So if this is going to 0, 0 times 120 gamma is 0. So the only term that this limit will settle to is 120 gamma because it doesn't have a variable t. So it's just a constant, right? Limit of a constant is just constant. Okay. I hope that makes sense. Okay. All right. So any other questions on this? So the next, let me know if you guys have any other questions. Okay, so Liana, you're answering. Okay. All right, so the next type of application that we're going to talk about is compound interest. Okay, so this is still 2.3. So 2.3, we're studying two types of applications. One is a tank problem, and the second one is compound interest. So I was looking through WebWork, and I noticed they have questions on. So they have tank problem, they have compound interest, and they also have Newton's law of cooling. You can ignore those questions, the one involving Newton's law. But if you want to do them, you can sure go ahead and do them. But I wouldn't require you to do them for this course. But up to you, those are optional. So let's get into compound interest. So this is the second type of application to first order differential equations. Liana, I would definitely do another problem, but not right now. Maybe tomorrow. I want you to look at the homework problem first and see how you would approach these questions. And then we can do some more brief review tomorrow, office hours, okay? So if you want me to do more problems, I can do them during my office hours. But for now, I want to move on to compound interest. That way we don't fall behind in the course, okay? I hope that sounds good. Right, I have 2 office hours, Tuesday and Thursday. So whichever time you're available, or if there's another time you want me to come in and have a session, I can do that as well. So you'll have plenty of practice. Okay, so having said that, let's move to compound interest. So what are compound interest problems? Well, compound interest problems, they're pretty interesting. They're a set of more real world problem, right? So tank problems are nice, yes, but these are more like economic applications. If you make an investment, if you borrow money from someone and they charge you an interest, how much do you have to pay off by a certain amount of time? So those are the type of problem we want to talk about for this particular application, okay? So we have 2 types of growth. So two types of growth, or it could be a decay, right? So you might have seen this application in your previous course, probably in pre-calc. I'm not sure if you've seen calculus, but definitely in pre-calc you should have seen it. So we have type 1 where you have a linear growth or linear decay. So we have linear growth. If it's a linear growth, then we have, so I'm going to explain what these means in a few seconds. So I'm going to use the notation ds dt. Okay, so where s will represent the growth or the amount. Okay, so if it's linear, that means your slope is always constant, right? So let's just call it a k, constant growth. Or if k is negative, then you have constant decay, okay? So we don't want to talk about constant growth and decay because it's too dry. There isn't much to talk about. So we want to talk about exponential growth or exponential decay. So second type will be exponential. So that would be the rate ds dt is equal to r times s. Okay, so let me explain what this means. So r represents the rate. So it could be an interest rate. It could be interest rate. If you borrow money from someone, they charge you some interest. So r will be that interest factor. And s is the amount. So you can say current value. Right? Or some kind of amount. Okay. So if it's an exponential growth, then we're assuming the graph of this would look something like this. That's the exponential that we're familiar with, right? Now, let me give you a definition of what is an exponential growth. So here's the formal definition. So we say s of t is grows or decays exponentially if the derivative s prime is equal to r times s, where r is some fixed rate. So it can, so my screen disappeared. This can also be written ds dt is equal to r times s. Okay, so that's what it means to be an exponential growth or decay. Now, what if we do this? So what if, right?
Professor, can you reset your mic? You're cutting on off and on.
Okay. All right, so I hope this works. Thank you for letting me know. Right, always let me know if something doesn't go right. So is this better, guys?
Yes, thank you.
All right, perfect. So what if we add a constant factor to this differential equation? So this way. So if we assume some change in this model s of t by a fixed constant, let's say k, right? Then we obtain the following formula. So we have s prime is equal to r times s plus some fixed constant k. Okay, well, what does this k represent? So the k can represent two things. So it could be a deposit, right? If k is positive, meaning you're starting with some amount and every year you're adding an extra k amount to the account, okay? Or you're withdrawing some k amount every year. So it depends on the scenario. Or it could be a withdrawal. So that would be a negative k. So that's the model we're heading to. Now here's the big question, right? Here's the question. What is the solution to this? So solution would be s of t, right? How do we compute that function s of t? So before we compute, I'm going to give you some notation, what all of these variables represent, and then I will give you some background from pre-calculus, where this is coming from, and then I will give you the solution, the function s of t that represents this differential equation. Okay, so that's where we're headed. So let me give you some notation before I start more info on this. So here is some notation you should be familiar with. So first, S naught, that's going to be some deposit in a bank account, right? If you're making saving, then that's what S naught will represent. Or think of it, S naught is an initial amount, okay? So think of it as this would be the initial condition. So it will be the original amount or initial. So that's what S naught will represent. The second notation you should be familiar with is this function s of t. S of t would represent value of the investment at any given time, okay? So s of t is going to be the value of the investment at any time t. So you can think t is time, okay? Now what does ds dt represent? Right, that's the rate of change. So that's the rate of change of the value of the investment. So it's the rate of change of the value of the investment. So that's the differentials. They'll describe the change in the investment amount. And fourth, we should know what K is, right? So K, we mentioned it's a fixed constant. Now again, it will vary. If you're making deposit, it's positive. If you're making withdrawal, it'll be negative. So K will depend, but it's just a fixed constant. Okay. So it could be a deposit value or withdraw. Okay. And the last thing is little t. T represents time. Okay. So these are the notation we want to be familiar with for compound interest problem. Now let me give you some background. So let's revisit pre-calculus. Where is all of this thing coming from, right? So the cool thing is you're always connecting to the past. What you have learned so far. So let's recall from pre-calculus or calculus, wherever you saw this. So let's think of it this way. So I'm going to give you one new notation, but again, this is just for the derivation purpose. But we're going to stick to these notation when we work through these type of problem for this section, okay? But just for derivation, I'm going to give you one extra notation. So let's consider the following. Let's consider A naught be invested at, So at 6% per annum. Okay. Then the principal S of t at the end of 1 year will be, so your amount, it's going to be, so think of it this way. If you're investing some amount A naught, after 1 year, you are going to earn A naught times the interest. 6%, that will be 0.06. So that's the amount you get after a year, right? In a saving account, if you're making saving. So I hope this makes sense. So if I rewrite this, this would just be A naught 1 plus 0.06. So that's the amount you get after 1 year if the interest is compounded annually, right? So you will have this if interest is compounded annually, right? That just means once a year. Now what if the interest is compounded semi-annually? Semi-annually means, what does that mean?
Isn't it every 6 months?
Right, so that means twice a year, right?
Okay.
Yep, so thank you. So that means S of t is going to be, so here's what happens. We have some initial amount that we're putting into saving, and then we have 1 plus, so if I'm compounding it semi-annually, I have the rate over 2 to the second power, okay? So this would be the amount if interest is compounded semi-annually. Okay, right? And then you can keep going, right? You can generalize this. What will be the amount if you compounded quarterly, right? Quarterly means quarters, for every 4 times a year, right? So that would be A naught 1 plus the interest over 4 to the 4th power. So this would be the amount if the interest is compounded quarterly. Okay. And then we can also compound it monthly, weekly, and so on, right? Or daily. That's pretty cool if you compound it daily, right? But of course, no bank does that. So let me just give you one more monthly. And how would that look like? So that would be A0 times 1 plus the interest over monthly, so that's 12 to the 12th power. And so this would be the amount if the interest is compounded monthly. Have you guys seen this before? Like any other course? Maybe in economics? Okay, so Jay said no. All right, so if you haven't, no worries. This is just refreshing you where this is going, okay? So if you ever want to make any type of saving in the future, you can calculate, if you know the interest rate and how the interest is compounded, if it's semi-annually, quarterly, monthly, weekly, daily basis, you can calculate how much you're going to have at the end of 1 year, 2 year, and so on, right? So it's pretty good application to study. Now, what if we want to generalize this, right? So you can see the pattern and kind of come up with closed formula. So this would be S of t if the interest is compounded monthly. So, and in general, so the principal which is the function S of t at the end of say 1 year will be, so we will have S of t is equal to some initial amount 1 plus the rate over m time to the m power. Okay, so that's the formula we can sort of generalize this into. If, so will be this, if the interest rate r percent per so Liana, you remember this, that's good. Glad you can remember this stuff from the past. So so again, you'll see everything connects. So materials you learn in the past courses, in any math course, it always relates to the future courses you take. Okay, so that's the good thing about a math course. So let me finish writing this. So this would be our model if the interest rate r% per annum is compounded m times per year. Okay, so that means at the end of t years, it will be the following. You'll have S of t is equal to a naught 1 plus r over m times t. That will be the model if we compounded m times per year. Now, what we want to do in this course is we want to compound it continuously, meaning at every instant. Okay, so this is what's going to happen. So compounded continuously, we let m go to infinity. Okay, because you want to compound it at every instant. So what do we have? We have the following. So we're almost there. We're looking for this magical function S of t, right? Because that is the solution to this differential equation we have. Well, not this one, really this one right here. S prime is equal to r times s without the k factor. When it's added k, we're going to modify it. So what is the solution? Well, the solution is this S of t, but we want to compound it continuously. So we take the limit as m goes to infinity. And that will be our final stage for this problem. So observe what happens. So m goes to infinity, we have S of t is equal to the limit as m approaches infinity of this entire formula. So a0 times 1 plus r over m to the m times t power, right? Now, to take this limit, we're going to do something cute, okay? So what I'm going to do, I'm going to make you recall something from the past again, but I'm going to modify it before I do that. What I'm going to do, I'm going to divide this by r and multiply it by r at the same time. So I maintain 1, okay? So if I do that, observe what happens. So you have, so a0 is just a constant. We have the limit as m approaches infinity of 1 plus r over m to the power, so I think I'm m over r and to the power r times t. So I just rewrote it in such a way so that we can identify what is this limit. So what do you recall? What is this limit? What is this limit right here? Do you guys remember? So if you remember from calculus, this is the definition of e, right? The exponential term. So this is e. So what we really have is, now where is this e coming from? So from calculus, if you remember the limit as, so in calculus, of course, you use different notation. So I think you saw it this way, 1 plus 1 over x to the x power, right? This limit is e. So what we have is we rewrote it in terms of r and m, but of course there's just any constant. But you should be able to recall this. This limit is e. So what do we have? We have of t. So thus the solution that we're after is a naught times e to the rt, right? So that's the magical solution we're after. So it's the exponential, right? So if you look at it from previously, right here, I mentioned if you're looking at an exponential growth, then the graph is this tiny graph I drew, and that's the graph of an exponential function. So the solution to this differential equation is nothing other than this exponential function multiplied by some initial value a naught. So that's pretty cool, right, guys? Any questions or comments? But of course, we want to apply the method of differential equations to get to this solution, right? So let's do that. So we know the solution, how it looks like, but let's do it in our way. So in our course, we're going to solve it the following way. So we're trying to find solution to ds dt is equal to r times s, where r is a constant. How do you solve this differential equation? Which method do we apply?
Separable.
So we want to find solution to this. And this is separable. So we're going to go ahead and use the separation of variable. So we have ds over s is equal to dt times r, and we integrate both sides. So we have ln of s is equal to r times t plus a constant c. So again, I'm going to assume s is positive so I can remove the absolute values. So we exponentiate both sides, so we have s of t, so is equal to c times e to the rt. And that's exactly what we got here, right? Except, of course, we're using a naught and c, but they're just any constant. So that's the solution we were after. The solution to this differential equation is this exponential. And of course, if you want to modify, you can just put this to be s naught. So any questions up to here? Now, what if, so now what if we involve k? What happens to it? So then we're solving ds dt is equal to r times s plus or minus k, right? Well, what is the solution to this differential equation? So what is s of t now? How do you solve this one? What do you guys think?
Do we use the integrating factor for this?
Right, so Shimon, you're correct. This is linear, so we can use integrating factor, right? So if I use, so let's find solution to this. So we're going to go ahead and subtract rs both sides. So we have ds dt minus rs is equal to k. So mu of t is going to be e to the integral of negative r dt. So that will be e to the negative rt. So then our differential equation becomes the derivative respect to t of mu e to the negative rt times s of t is equal to k times e to the negative rt. Okay, and then by integrating both sides, we have e to the negative rt times s of t is equal to, so if I integrate the left side respect to t, r and k, they're just constants. So this would give us negative k over r e to the negative rt plus a constant c. And then finally, by solving for s of t, we have, so I divide both sides by e to the negative rt. We have negative k over r plus c e to the rt. So that's the solution if you add in a k factor to the differential equation, okay? But if you put a minus k, this would change slightly, right? So I'll put that on the side as well. So let me know if you guys have questions. So a lot of you are very quiet today. Let me know if you guys have questions. So if k is negative, how would the solution look like? What do you guys think? So this is the solution before plugging in initial condition. Of course, when you plug in initial condition, s of 0 equals s naught, this will get modified, right? So we have to keep that in mind. So going back to my question, what if k is negative? So, all right, so Sadia, thank you. You're processing, that's very good, right? So again, let me know if you guys have questions. I know it's allowed to take in for 1 hour and 40 minutes, but we just have to keep going, okay? Just make sure you pay attention and keep track of what's going on. So my question is, what if the k is negative? What happens? Then we have the following model. We have ds dt is equal to r times s minus k. And then you keep going with the integrating factor and so on. So the only thing that would change is this factor right here. That's the only thing that's going to change. So again, if you want to memorize it, you can memorize it, but I would say don't memorize it, just derive it. It's not hard to derive. It'll just take you an extra maybe 30 seconds or 60 seconds. You'll have s of t to be c times e to the rt plus k over r. And then you plug in initial condition s of 0 is equal to s naught. You'll find what is c. So that will be your formula if k is negative, and the left side box will represent the solution if your k is positive. All right, so any questions up to this point? so we did the derivation. Now I'm going to do a problem. So how do you guys feel? Okay. All right. So Greg, you're pretty good at it. Good. Tough. All right. So Wasi, don't feel overwhelmed. It's okay. Just take your time. Okay. Take your time. And now let's do a problem. Hopefully things will fall in together as we see how to approach these formulas when we see an actual scenario. Okay. So let's work through an example. So here's our first example for compound interest. So suppose that a sum S naught is invested at an annual rate of return R compounded continuously. Okay, so compounded continuously should give you a hint that we're using this model right here. S of t is equal to CE to the RT, okay? Or you can think of you're solving this differential equation. ds dt is equal to the rate times the amount, okay? So, all right, so we have a scenario. Now let's write down some parts. Part A, we want to find the time t, big T, required for the original amount to double. In values as a function of R. Okay, so that's the first part. So part B, we want to determine T, again, T is for time, if the rate is 7%. And part C, we want to find the return rate that must be achieved if the initial investment is to double in 8 years. Okay. All right, so let's see if we can work through this problem. So this is a compound interest problem, right? So we're working with dt is equal to r times s plus or minus k. Now, does the question mention about any amount you're withdrawing or depositing?
Nope.
No, so that means k is 0. So we can write off from the back, we can start with ds dt is equal to r times s because k is 0. It doesn't mention in the question, so let's drop that factor. Well, we know what's the solution if ds dt is equal to r times s, right? So this is something you can always, again, compute. by doing separation of variables, or you can memorize it's just the exponential to the e to the rt, right? So we know part A, so let's write down the answers to this part. So for part A, so maybe I should use different color, right? So I'll give you guys a few seconds just to, you know, understand the problem. So we're working with the model ds dt is equal to r times s. This is separable. So you can go ahead and separate the variable, find the solution. But we know this is just the function s of t is equal to c times e to the rt. Where c is the initial condition, right? So initially, what's given to us in this problem? So what does this represent? So what does s not represent?
Would that be our constant in this case when s is equal to 0? That's
Right, so when time is 0, right?
yes.
Yeah, so correct. So we have our initial condition, right? So we have s of 0, that's s naught. So if I know the solution, I can plug this in and find c. So if you plug in t equals 0, s naught is equal to c. So that means our model is just s of t is equal to s naught e to the rt. Just rewriting stuff. Now, rate, we don't know. It's just some r. And what do we want to find for this question? Part A. What is it asking us to find part A? We want to know the time for the original amount to double as a function of r. So we want to find t, the little t, but you can replace it with the big T, right? So we want to know what is t, right? When the amount, so I can also write it this way. S of big T, when it's going to double the initial amount. Initial amount is S naught, so that's 2 times S naught. That's what it means to double, right? So let's plug that in. So we have S of T, that's going to be 2 times S naught. So I'm going to plug this in here. So we have 2 times S naught is equal to S naught e to the R times T. And then you want to solve for T. So I will divide by S naught. So we have 2 is equal to e to the R T. And then how do you solve for T from here?
ln both sides.
Yep, so we have T is equal to, so if I ln both sides, I have ln of 2 and then divide by R. So that's our T as a function of R. So that's the time when the initial amount will double. Okay, so any question for part A? Now, what about part B? What do we want to know for part B? We want to know time. Well, we already know the time when it's going to double if the rate is 7%. So what do you think you have to do for part B?
Just plug
So,
in r is equal to 0.07.
yeah,
Into
so we
the
just want
function.
to know. Exactly. So we just want to know T. If you plug in the rate is 7%, 7% converted to a decimal, that would be the setup. So the T would be ln of 2 over 0.07. That's part B. Okay. And part C, we want to know return rate R, right? So that means you're looking for R that must be achieved for the initial investment to double in 8 years. Well, we already know the relationship between T and R when it's going to double. That's the first part. Now we want T to be 8 so that we can find what is R, right? So basically you're plugging in T is 8 and looking for what R is. So we want to know R when T is 8 because we want the value to double. So that would give us 8 is equal to ln of 2 over R. So that means R is equal to 1/8 ln of 2. So that will be the rate for the amount to double in 8 years. Okay, so that's one type of questions when there is no withdrawal or deposit being put into an account. Okay, so that's one type of application. Let me give you another example. Any questions before I start writing the next example? Does this make sense?
It makes more sense with the example.
Okay, all right, that's good. Okay, so Imrose, you said why k is 0. So the reason k is 0 in this problem is because it doesn't mention if the individual is withdrawing or adding extra money to the account. It doesn't mention, so we assume k is 0. Okay. All right, any other questions? Okay, so Liana, thank you. All right, so here's another question. I'm gonna write it out, but I'm probably not gonna finish it today because we only have 5 minutes. So I'll have you think about it before next class, so at least you'll have something to think about tonight. So here's our second example. So suppose Jerry is depositing money into a bank account continuously at the rate of about 10,000 per year, and the account earns interest of 4% annually. So this is a compound that continuously okay. So Jerry began his first year with 23,000 in the account. Assuming he doesn't make any withdrawal. How much money is in the account after 3 years? Okay. So here's a question that I want you to think about for next 24 or 23 hours, whenever you have time. And then continue with your web work assignments as well. So we'll continue here next time. Okay. All right. So do you guys have any questions before we finish our session for today? Okay, so we have just a minute left. Right, so yeah, I could do that, but the thing is my device, I have to keep flipping back and forth to go back to my OneNote screen. But yeah, I would consider that next time so we can do more problems just by doing copy and paste. Thank you. All right, so yeah, let me go back. So I'll post the notes on my website and the video as well. So if you want to think about this question for tomorrow, we'll start from here next class. All right, so do you guys have any questions? All right, so we'll finish our session for today. You guys stay well. I will see you all tomorrow.